turning on recording. Okay, share. Share screen. Okay, screen shared, hopefully. Okay. Okay, you guys should see IB Physics topic 4.5 standing waves, correct?
Yep.
Yes.
Okay. Okay, so starting. In terms of objectives, topic 4.5 is all about standing waves. This was waves on a string, open closed tubes, open air tubes that we covered last year. So there's nothing really new in this unit, except we might go in a little bit more depth. Under understandings, the IB wants you to understand the boundary conditions and the definitions of nodes and antinodes effectively, which we've already discussed last year. Where it goes into a little bit more depth is we're going to talk more about how the standing waves are created, why they're created that way. Okay. Under guidance, it lists all these. There's quite a bit in the way of guidance. There are no formulas. Okay. Last year we had formulas on the on our formula sheet. For whatever reason, the IB said all those formulas gone. Okay, you need to understand and be able to derive the formulas in this unit yourself. Okay, and those formulas are based off of the boundary conditions that we talked about that are listed here. It's basically they're the same for strings as they are for pipes. You just need to know how to apply them. Okay. And the other aspect we're going to talk about are the various harmonics. Once you know what the harmonic is, you can calculate what the wavelength in the medium happens to be. Okay, apply that either with the frequency or the speed of sound or the speed of the wave at least, and do the rest of your calculations. Okay, so that's where the challenge in this unit is going to be. You need to be able to derive those formulas. Okay, definition-wise, we're again heavy on the definitions. All of topic 4, it's definition after definition after definition. You need to know what the words that they are using are. Okay, so, and then if it's up to you to write something, the more you use these words and use them correctly, the more likely they'll be like, hey, you know, Andrew knows what he's doing on this. I'm going to give him full credit on this, even though I can't read the rest of the stuff. Okay, so definition-wise, superposition. We use superposition in all sorts of areas within physics. It's basically add two things together or add the multiple things together. We use superposition for electric fields. We use superposition for magnetic fields. We're also going to use it in terms of waves. All it means is we add the two amplitudes at that point in time and space together. Interference is a more general term. It's basically just what happens is the result of two or more waves in colliding or overlapping at the same point. If we use the term constructive, it's greater in amplitude. The result is greater in amplitude than the component waves. If it's destructive, it's smaller in amplitude than the component waves. Okay, so constructive is basically what happens when the two waves are on the same side. They're both positive waves or they're both negative waves. Destructive basically requires one of them to be positive, the other one to be negative. A standing wave is a specific type of interference, okay? It is interference. It's what happens when one wave is traveling one direction and the other wave is traveling the other direction. They must be the same frequency, okay? And it basically, if you get it just, what happens then is you end up with these points of zero motion. Okay, those points of zero motion are called nodes. Okay, and then you'll have points of maximum motion called antinodes. The only other definition you'll need here is reflection, and reflection does two things. Okay, primarily it changes direction. Okay, but there are situations where it will also change the phase of the reflected wave compared to the incoming wave. Okay, so talking about that reflection and the phase, okay, why and when does it change phase? Okay, it changes phase 180 degrees. There's nothing else. It's either 0 or 180. Okay, whenever the wave is coming in from a lighter medium and hitting a denser medium, it could be something as dense as a wall, okay, or something as dense as just slightly more dense, like a heavier string. Okay, in that case, what happens is the wave gets reflected 180 degrees. The reason it gets reflected 180 degrees is when the wave hits the wall. We'll use the wall as an example. Okay, the wave is effectively pulling upwards. Okay, it's exerting a force on that point where it connects to the wall. Well, guess what that means? Okay, what that means is Newton's third law says, well, if it's pulling up on the wall is pulling down on the rope. So the wall is basically putting a opposite side wave back on the rope, and that's what you see traveling back. That's what the reflection happens to be. The wall pulling back on the rope. On the other side, the right-hand side, is what happens when I'm going from a denser medium to a lighter medium. Okay, so in the upper case, there is no connection. Okay, it's basically free to move. Okay, so again, the wave comes in and it hits the end, but now there's no wall to pull down on it. Okay, instead, it's a matter of just the action of the free end of the rope, and so it still gets reflected. That reflection sends it back on the same side, so there is no phase change associated with this when it goes from a dense medium to a lighter medium. Okay, and it's this difference between dense, it's this 180 degree phase change difference that results in the situation we have with an opened closed tube versus an open air tube. Okay, this is why the open side of an air tube represents an antinode. The closed side of an air tube represents a node, and we'll talk about that coming up. Okay, superposition. This superposition is actually a part of topic 4.3. Okay, but I didn't think it made sense there, so I moved it into 4.5. Okay, and basically when two waves overlap in space, their amplitudes are going to sum together. You are going to need to basically graph out a situation when two waves overlap. What does that look like? What does it look like when this wave is going to the left, this one's going to the right, and then they partially overlap? And so I'm going to go and give you an example here. Okay, you should see kind of okay, a blue wave and an orange wave on the top screen here. Okay, if I animate them, okay, they start moving towards each other, and then at some point they overlap. Okay, and then they keep going, because a wave is just energy. The waves don't, the energy doesn't bounce off of each other. They keep going. Okay, on the bottom, if I show you what this wave looks like when they, come on, reset. Okay, so on the bottom is what the actual string will look like. Because the waves can't the string can't be in two places at the same time, the waves, when they overlap, will look slightly different. Okay, so look at the bottom screen, and I'll pause it just as they start to overlap. Okay, so right here, they're just starting to overlap, and the string is going to look very weird. Okay, and if I do one step at a time, okay, this is what happens when they're slightly overlapped, halfway overlapped, in fact. The string takes this form, because right here in the middle, okay, it's a 0 plus a 2. So 0 plus 2 gives me this dot. Okay, just 2 squares. The next one over is a 3 plus a 4. So all of a sudden I go all the way up to 7. 1, 2, 3, 4, 5, 6, 7. So that's, and then I draw a straight line between those 2 dots because that's the best I can approximate. Okay. The next one over is 8. And the next one over is 0 plus 4. So it's over here. So you need to kind of do that. Just move the waves 1 square at a time, or 2 squares, or whatever it's asking of you. Okay, and then when they're overlapped, simply add the amplitudes. Okay, it goes 0 plus 4, 0 plus 3, 0 plus 2, 3 plus 4, 4 plus 4. Okay, and just plot it out. It's kind of like just drawing the dot to dots that you used to do, back in 2nd grade. Okay, and that's the way, superposition will work. Okay, even to the point where if I choose opposite graphs, okay, I can make them, when they overlap, totally disappear. So on the bottom is my overlapped wave. This is what happens when you have a node. This is total constructive interference. Total destructive interference. Okay, the wave is completely gone until I keep moving, and then it starts to show up again, and the waves continue in their motion. Okay, now it's going backwards. Okay, stop. No. Okay, so back to the PowerPoint. Okay, interference, when we talk about like sound waves and sine waves, okay, in this case, we still have constructive or destructive interference. Okay, in this case, my waves are both going from the left side to the right side of the screen. Okay, when they are in phase, basically meaning they're both at the same phase of their sine wave. Okay, it's constructive interference, and I simply end up with a bigger sine wave, one with twice the amplitude. If they're 180 degrees out of phase, when they sum together, it's always going to be 0 at all points in space. Okay, so it's basically, well, nothing is happening, and even though there are 2 waves on this string, you just can't tell. Okay, so that's what I have with destructive and constructive interference. But these waves are traveling in the same direction. So in time, they either both go up at the same time, or one's going up and the other one's going down. What happens when they're going opposite directions, however? Okay, when they're going opposite directions, okay, one may be going up and the other one may be going down, but sometime later they're both going up, and then sometime later they're both going down. Okay, and if you do this correctly, okay, as long as they're the same frequency, you will always have this situation of nodes and antinodes. Okay, so again, off to another demo. Okay, so in this case, the red wave is going to the left, the blue wave is going to the right, okay? And it really doesn't matter, as long as my frequency or wavelength is the same, and the wavelength will, if the frequency is the same, the wavelength must be the same. The amplitude doesn't matter, okay? But the wavelength must be, or frequency must be the same. Because they're both in the same medium, their speed is the same, so frequency and wavelength correspond. Okay, so I'll set this in motion, and you can kind of see on the bottom here, okay, right here where my cursor is, hopefully you can see that. Okay, that's a node. That point, that purple point is never moving. Okay, I have multiple of these nodes. Okay, there's another one over here, and another one, and the ends are also nodes. Okay, so if this was a string, let's say a violin string, this is one end is the bridge, and the other end is, I forget where where the string starts to connect to the peg. Okay, those points can't move. Okay, maybe it's being held down by your finger because you're playing a note. Okay, but and that's why the violin strings set up standing waves, because it reflects off of one end, comes back, keeps reflecting back and forth. Okay, and you end up with this special situation. Okay, if I change my wavelength, okay, I'm going to change it to 3 and change the other one to 3. Okay, so I changed my wavelength now. It is now 3. Okay, and so if you look at this, again, I still have a standing wave. This point is still a node. Okay, this is a node. I still have this antinode aspect. Okay, but if this was a string, okay, it fails what is called a boundary condition. What is that boundary condition? That boundary condition says one end must not be moving. I'm holding the string down with my finger playing a note. Okay, that must be a node. The other end stuck on the bridge of my violin or guitar or whatever instrument I happen to be playing. Okay, and so if I'm holding it down, it can't be moving. Like this is moving right now. It's moving on both ends. Okay, it actually looks like it's an antinode, but it's actually not. It's a little bit less, it appears, because it's not going quite as far as it should. Okay, so this wave would not exist on my string. Okay, so for a standing wave to exist, it must match the boundary conditions. Either the end must be a node or the end must be an antinode. When you pluck a string or bow a string or strum a string, you're actually putting on effectively an infinite number of frequencies on there. Most of those frequencies will die out except for the ones that can form standing waves. Because with a standing wave, that energy just keeps bouncing back and forth. Okay, with a non-standing wave, that destructive interference starts to kick in, and it doesn't bounce back and forth. It dies out, and so all you really hear, okay, is the ones that are formed by standing waves: the first harmonic, the second harmonic, and so on. Okay. So getting back to this picture, okay, you're going to need to interpret these types of diagrams. Okay, and so that's what the rest of this unit is going to be about. Okay, first, before we get there, a couple more definitions. Okay, for IB's purpose, really only the first 2 definitions are needed. The first harmonic is the lowest frequency or the longest wavelength standing wave that matches the given boundary conditions. Okay, some of you more musically inclined may also call this the fundamental. Okay, IB says they will not use the terms fundamental. Okay, they will also not use the terms overtone. Okay, every harmonic after the first harmonic, the second, third, fourth, etc. Okay, I call it the nth harmonic because n is an integer. Okay, it basically takes the frequency and multiplies it by n. So the second harmonic is twice the frequency of the first harmonic. Okay, same with the third harmonic. It's 3 times, 4 times, 5 times. Okay, you may not have every single harmonic present. Okay, this is especially true for the open-closed air tubes that we studied last year. Okay, in those cases, if you remember, only the odd harmonics were present, none of the even harmonics. Okay, the second harmonic doesn't match the boundary conditions. The fourth harmonic, same thing, doesn't match the boundary conditions. Okay, besides that, for those of you more musically inclined, again, overtones are any standing wave that is greater than the first harmonic. It is different, okay? Most instruments have overtones that are different from the harmonics. Okay, for a violin, it's because the violin has its specific shape. So you'll get harmonics going horizontally across the wood of the violin as opposed to just the string. Okay, and it's the overtones that give an instrument its timbre. Okay, what makes a violin, even though it's playing the same note, sound different from a clarinet, sounds different from a trombone. Okay, it may be the exact same note, but many of you could say, hey, that's a violin. Hey, that's at least a brass instrument. Okay, so getting to the boundary conditions, there are basically only two types of boundary conditions. One boundary condition says this end is a node. The other boundary condition says this end is an antinode. Okay, and the way to determine whether it's a node or an antinode is to ask yourself, can this point move or can this point not move? Okay, if it can't move, it's a node. If it can move, it must be an antinode. Okay, and so those are the two boundary conditions. For a string, it's almost always the ends are going to be nodes. Doesn't have to be. I can hold a string vertically and wiggle it, and it will reflect off of the end of the string that's free to move. Okay, and it will reflect on its way back up. Okay, so that's what happens. So it doesn't have to be, and for whatever reason, the IB says we're going to deal with the open situation for a string as well. Okay, so just always ask yourself, must it be a node or must it be an antinode? Same thing for an air tube. Okay, we're only going to look at strings and air tubes. For an air tube, if the end of the tube is closed, it's blocked off, air can't move at all. Okay, it's hitting a wall, and if it can't move, air movement must be a node at that end. On the open end of that air tube, air can move as much as it wants. Okay, and so that air end must be an antinode. Okay, so going on to the eye diagrams. Okay, I call these situations eye diagrams. This thing where you have two sine waves, 180 degrees. Okay, it's just one string, but it's showing the string at its amplitude points. Okay, sometimes they'll even show you points inside the eye. Okay, but one single loop, okay, which is just this point here. Okay, one single loop, which is just this. Okay, that represents half a wavelength. Okay, not a full wavelength. Okay, so just remember that the loop represents half. The other half, it continues on. Okay, you may not even see it. Okay, but this is the second half of that wave. Okay, remember, a wave has to go, a sine wave goes 2 pi radians. Okay, it has the up positive part, and then it has the negative part. So one wave or one loop is only half a wavelength. Okay, and points in that medium, because this wave is a sine wave, okay, points in that medium experience simple harmonic motion. So if let's erase these things. Okay, this green point here is undergoing simple harmonic motion, up and down and up and down and up and down. It's not moving left or right, it's just moving up and down. Okay, because it's a wave on a string. If it was a sound wave, yes, it might be moving left and right. Okay, this blue point here is also undergoing simple harmonic motion. Okay, it has a different amplitude, however. Okay, the amplitude of that blue point is less than the amplitude of the green point. If the green point is at the antinode, it's got the greatest amplitude. That blue point, a little smaller. If I had another point, this point would be even smaller. Okay, sometimes the IB does get a little tricky, and they ask you which one has a greater amplitude. Okay, they're talking about the points in the medium. You need to be able to distinguish between the amplitude of the standing wave and the amplitude of the points in the medium. Okay, So you do need to read their questions fairly closely because I've seen them get really tricky. Okay. So with the boundary conditions, okay, if you're trying to figure out the formulas or trying to figure out what the wavelength or the frequency is, okay, a lot of times they'll give you the speed of the wave, or that's what you'll have to figure out. Okay, V equals F lambda still applies. Okay, the frequency of the two waves going forth equals the frequency of the standing wave. Everything must be the same. The frequency of the wave going to the left must be the frequency of the wave going to the right, must be the frequency of the standing wave. Okay, so establish those boundary conditions. Is this end a node or is this end an antinode? Okay, after that, draw the smallest number of eyes that can fit that situation. Usually it's just one eye, okay? In the string node-node situation on the left, okay, it's basically just one eye. If you freeze it at the two furthest extremes, it's one eye, okay? The lower right-hand corner, which is an open air tube, is also one eye, but it's two halves of an eye. Okay, so it's still the same thing, but you have to, the antinode ones are the harder ones to draw because you actually have two waves there. Okay, one wave at one maximum, the other wave at the other maximum. Okay, so as you draw this wave, just remember it has going from one antinode to another antinode. It starts at positive maximum, positive amplitude, down to a negative amplitude. Okay, same thing with the closed open. Okay, in this case, I have only half of an eye. So half of an eye is half a wavelength or a quarter wavelength. Okay, and so these are how you must, I would operate in terms of drawing and deriving the formulas necessary to solve the problems associated with this. There are no formulas in the formula sheet, again, I have to remind you. Yes, if I gave you a test on this, you could probably memorize the formulas and use them. Okay, but next year when we're doing this, it'll be a little bit harder. Okay, so once I have the eye diagram, how do I calculate what the wavelength is? Okay, if you know the length of your medium, okay, either string or an air tube, okay, just determine how many wavelengths are in this picture. Okay, if I have a fundamental, it's just in the uppercase, okay, it's half a wavelength, or lambda over 4 equals the length of my tube. In the bottom case, I have two halves, but basically it's one eye, so lambda over 2 equals my length of my medium. Okay, and that gets me my fundamental frequency, or the first harmonic. And as long as I have the first harmonic, I can figure out what all the other harmonics are after that by multiplying my frequency by n. Okay, just remember, for the open-closed situation, I only have the odd harmonics. Okay, and so if I wanted to look at what my wavelength is, okay, the wavelength for the top one, okay, my wavelength equals 4L. It's basically just solving this equation here. Okay. It's just solving this equation. And if I did that, lambda is going to equal 4L. Okay. Going to the third harmonic, because the second harmonic doesn't exist. The second harmonic would require me to have a node on one side and a node on the other side. Doesn't exist. I must be node antinode. Okay, so that's why I go to the third harmonic. That one does exist. In this case, it's lambda equals 4L divided by 3. I'm just solving this equation. Next one, lambda is equal to 4L divided by 5, etc., etc. Okay, so wavelength, basically, in the general case, my wavelength is just going to be 4L divided by n, the harmonic number. Okay, because this is 4L divided by 1. Okay, And so you can derive these formulas that we gave you last year fairly easily if you know how to approach that. Okay, frequency is just the multiplication. So here we have the third harmonic, the fifth harmonic. Okay, just multiples of the first harmonic. Okay, and so the formulas are easy to derive. Then simply applying V equals F lambda after that gets you everything else that you need. Okay, anybody have any questions at this point? Because that's the end of the presentation.
Nope.
Okay, I'm gonna stop sharing. So at this point you have, okay, so somewhere in the middle, I missed when Rohan joined, but he did. I assigned you a whole bunch of textbook problems. Okay, I want to say it was like 17 problems. Most of them are fairly easy. It's kind of like here's the frequency and the wavelength. Find me the speed of sound or something like that. Easy, but it is more than usual problem. So it basically covers problems. So if I'll leave 4.4 off entirely, I'm still planning on covering it. But if I can throw that over to Dr. O, he'll probably review topic 4 anyway before going into topic 9. Okay. So yes, it is a lot of questions. It is not due at midnight tonight. Okay. You are lucky in the sense that you have the weekend to do these problems. Okay. A day will not luxury. But I am also giving you 2 periods to do it. Not due at the start of next class, due at the start of the class after that. Only because it is a lot of questions and not everybody works fast. However, okay, there's always a however. I'm recording stuff. You will have a lab. I'm going to do the lab here at home. I will collect or show you what all the data is, and you must calculate the speed of sound in air given that data. Okay, so I'll put that all together, and that will also be due the class after. So if you wait until the last minute, and I know there are some of you that take it as a challenge to see if I can do this, how much last minute can I do this? I know there are some of you that love that challenge. I'm recommending to you or suggesting to you, okay, try to get this homework done over the weekend. Okay, because otherwise you will have both the lab. Now the lab is fairly short, okay, but you will have both the lab and the homework to do for the last class. It's basically I will see you on Thursday of next week. Okay, Tuesday and Thursday. Lab on Tuesday. This is due on Thursday. The lab is due on Thursday. Is probably when I will start topic 4.4. So there's no breaks. We're going to be going right. I'm going to be teaching right up to the end. Okay. Anybody have questions before I let you go? Okay, if there are no questions, I'm going to let you go. I'm going to stop recording. Video should be available